Let's talk about Romberg's method. This will be our last video about Romberg's method. We started with an idea and now we come back to that idea. I told you this is an idea, and then I told you Romberg looks completely different, but in the end we will come back. And what do we see? Romberg is exactly doing that what was our first idea, but with a slight modification due to the fact that we have only even hypotheses, so we will modify that a little. So we can take the trapezoidal values. Let's say we start with h is a half, then we get a trapezoidal value, then take a half, get a new trapezoidal value, and then take a quarter, h to be a quarter, take a new trapezoidal value, then interpolate these three values, and then evaluate at position 0. And doing the interpolation with a polynomial, and in this polynomial there are no odd coefficients, no odd potencies, then this is an idea we can follow. Here you can see the code. I'm using some function, doesn't matter which one. Then I get 4 values here in that example. So we have the value for 1, we have the value for a half, we have the value for a quarter, and we have the value for 1 divided by 8. And then here we have the polyfit command. It's impossible to tell the polyfit command. Please use only even potencies. So we can do the following trick. We modify the x values here in this special situation. This trick works. And then we get an interpolating polynomial. And evaluating this polynomial at position 0 means only that if you have a polynomial of that type and evaluating at position 0, you will get the absolute value, and polyfit returns the coefficients. The first one is the leading coefficient, so this one. The second one is this one, and the last one is this one, the absolute value. So evaluating is take the last coefficient. Okay, that's what we can do, and then we can also apply Romberg here, and then we get exactly the same result. And this is always equal, as I will show you now. Okay, so let's use some function, and now let's get the 4 trapezoidal values here. And here taking in the first time only 1 part, then 2 parts, then 4 parts, then 8 parts. It's not important that we start with 1 part. We can also start with 3 parts, but then the next step is 6 parts, 12 parts, and 24 parts. So always double. And then here we have these h's. We have now 4 values, and these belong to h to be 1 in the first case, a half, a quarter, and 1 divided by 8. Now here polyfit, get the polynomial of degree 3, interpolating these points, and here this trick, h, we modify h. So polyfit thinks he will give us a polynomial of degree 3, but instead we get a polynomial of degree 6 belonging to h, not h squared, but h, the values h and I. And then we compare, and then we compare. So let's run that code, but it's no surprise what we will see. And we see the 2 values are equal. But okay, let's use format long, then it's more convincing. And now let's run, and we see all digits are equal. So this is a very, very strong hint. Okay, being a mathematician, you say, okay, this might be a coincidence, so we can modify. So maybe we take that function instead of the one we had, and let's run again, and we see again completely the same values. Okay, let's continue modifying, and we will see always the same number. Here we have the last digit. This is not equal, but this has to do with the nature of floating point numbers, and the calculations which are performed in a little different way, and so the last digit may vary. Okay, this is very convincing, I think, but to be more convincing, I insert it here. N is 4, and so we can check if it's only true for n is 4, or if it's also true for different n. Then we have to modify here. We don't run from 1 to 4, but now we run from 1 to n. Here, the polynomial we are using to interpolate the values should be not of degree 3, but of degree n minus 1. And also Romberg, for the comparison, we want to take n stages. Okay, let's run that code, and we see again the same values. And now we can play around. Let's use a different n, and we see again same number, same number, same number, same number, same number. But now we get a warning, the matrix, when we do interpolation polyfit, then we get a matrix which is close to singular. So we should stop that with n is maybe 9 as also a warning, but for 8 it worked, and for 7 it works also. And we can also play around with the function, and we see always the same answer. So to be even more convincing, I said, okay, I want to visualize that. Okay, let's visualize the idea that you can really understand the point of that video. So here I start with that function. I start with n is 6, and then I inserted these lines. Let's do a plot of the trapezoidal values, and then let's do the plot in the end. And now we see what's going on. Okay, let's run that code. Here we have these trapezoidal values. If we have the function cosine of x squared and we integrate from 0 to 1 and we use the trapezoidal rule, then if we have only two values, one at 0 and one at 1, and then doing the trapezoidal rule, we get that integral value. Using 2 parts, we get that trapezoidal value. Using 4 parts, we get that trapezoidal value, and so on. And now it's more or less clear the true value is more or less 0.91. And now doing that, we see also that this is the interpolating polynomial as I show you here. First, I build the true interpolating polynomial. It's zeros at the odd positions, or at position 2, 4, and 6, because MATLAB, the index starts with 1. And then the coefficients belonging to the even coefficients are the ones of p. And then if we evaluate this polynomial, the interpolating polynomial, at all values between 0 and 1, we can plot that line in blue. And that's what we see here. And now we are interested in that value. And if we want to see that value here in the plot, we can do this, and we see it's 0.945. And this is that number, 0.945. Okay, that's what's going on. And now we can play around also here, and we see that. That's what's going on. Okay, to be even more convincing, I modified here. Let's play around with the interval. It can also be the interval 0 to 3 or 1 to 5 or whatever. And then let's kill the pause. And here I have also to adapt to the interval length. So let's run that code. And we see the following. This was the trapezoidal value if we take only one part. This does not make any sense for this high frequency function on this interval, so this is not a good value. I don't want to illustrate a real world application. In this case, this would not make any sense to use only one part, but I want to illustrate that Romberg is indeed the same as interpolation of the trapezoidal values and then evaluating at position 0. And so we see that picture, and we see here the values, and they are equal. Okay, so here also we can play around. And we can play around with the function, so maybe this function instead. And we can play around with the interval. Let's use b to be 6 or whatever. And we see it will always be the same value. Okay, so Romberg is interpolate the trapezoidal value and then evaluate our interpolants. So we extrapolate. And why is that true? We can see that it is true indeed, that it's the same, the absolute value of the interpolating polynomial, if you remember that here we did that analysis to find which combination should we take to get rid of these coefficients, and then in the next stage to get also rid of the h to the 4 combinations, and then we have f plus only potencies h to the power of 6 and more. And if we say, okay, we have that, then we have here some values, and then doing this calculation is nothing else than find the interpolating polynomial and evaluate at position 0, but that means find this coefficient, find this C0 coefficient. And that's what we do here. So it's really obvious. But maybe it's not completely obvious, so I will write down it once more, but you will see it's exactly what we have written here. Okay, so let's use an example. Let's use this example. We are interested in this integral value. Then we calculate the trapezoidal sums. Okay, these are, if we take h is 1, evaluate at position 0, evaluate at position 1, and then a half times the value at position 0 plus a half times the value at position 1 divided by 2 times interval length 1 in this case, and then we get this trapezoidal sum. Then we take h half of the initial interval length, so it's a half. Now evaluate position 0, a half and 1, and then a half times that value, a half times that value, and 1 times the value at position a half, and then times interval length half, and then we get, and doing that for a quarter, we evaluate 0, 0.25, 0.5, 0.75, and 1. And we have these 3 values. And then we can visualize that. And then we extrapolate this tendency and evaluate at position 0. That's our idea. So the interpolating polynomial is, okay, we say we want to interpolate with a polynomial of degree 4 and the odd potencies are missing, so a0 plus a2 times h squared plus a4 times h to the 4th power. So we want to find a0, a2 and a4 such that we interpolate these points. How do we find the interpolating polynomial? Okay, so we know 3 values, these 3 values. So if you use the h, this h, then, so if h is 1, then we have that value, so this should be the result. And now we have one equation, a linear equation, and now let's do the same for these two. And now we have 3 equations for 3 unknowns. So let's reformulate a little. So a0 plus a2 plus a4 is that. Then a0 plus a quarter, a2 plus 1 divided by 16, a4 is that. And here we have 4 times 4 is 16, 16 times 16 is 256, a4 is this value. And now we want to find A0, A2, and A4, and then we want to evaluate at position 0, but that means that we only have to find A0. So let's find A0 out of these three equations. And how do we do? We can do Gaussian elimination in the following way. So let's take 4 times this equation minus that equation divided by 3. 4 times this equation minus that equation will kill A2, and that's why we do it that way. 4 times that minus that is 3A0 divided by 3, so we have A0, this cancels, and here we have a quarter minus 4 quarters, so minus 3 quarters divided by 3 minus 1 quarter times A4. And now on the right hand side, 4 times that value minus that value divided by 3. That's what we do when we apply Romberg, and in this case we get the value. Okay, let's eliminate also A2. And again we get A0. Again this cancels. This is a reason why this was a good idea. 4 times that is 1 divided by 64 minus 4 divided by 64 is minus 3 divided by 64 divided by 3 is 1 minus 1 divided by 64 times A4. And here 4 times that value minus that value divided by 3, that is what we are doing when applying Romberg, and in this case we get 7469. Normally we also have a third equation, but we are also looking for A0, so that is enough. And now let's eliminate that, and then we get what we want. Okay, and here I wrote down what I did. 16 times this equation minus that equation gives here A0. This cancels, and 16 times that minus that is that. Here I wrote down the rounded versions to 4 digits after the decimal point. I did all calculations with more digits. Okay, and then we have that value. And so that means if we apply the Romberg tableau, we do only the calculation for the right hand side, but then in the end we get the absolute value of the interpolating polynomial of that type. This interpolating polynomial, we used that form due to the fact of the theorem of Romberg. We did not use odd potencies, but only the even ones. And then in the end we get A0, and this A0 is the polynomial value at position 0 interpolating these three values. So applying Romberg is nothing else than that. We can see it in that light. And that's what I wanted to show here. In the end, let's say again, Romberg is this tableau. Take the trapezoidal values, then 4 times the better one minus 1 times the worse one divided by 3, and then in the next stage 16 times the better value minus 1 times the worse value divided by 15, and so on. And doing that is the same, will lead to the guaranteed same result as this optical very easy idea of interpolating the trapezoidal values. Okay, so this was our last video about Romberg.